Good afternoon, everyone. My name is Azarkh. I'm here to present optimal detector size for optical wireless communication links with wide coverage, done together with Sarchin Liu, who is another PhD candidate, and Professor Jean-Paul Linnartz. And in recent years, as already was described, LED-based, laser-based systems attract a lot of attention due to very obvious and already thoroughly described advantages of RF systems. And there is a lot of research on the high bitrate systems that are done via lasers. And let's say what was described, that LEDs has certain limitations in their bandwidth, while lasers provide much wider bandwidth and thus higher throughput. So if we have a very broad modulation bandwidth, the limitation comes to the receiver side. And on the receiver side, there is a trade-off between the area of the detector and the bandwidth. And because if the detector size is bigger, so we have a very big detector, we can receive much more light, and we have great signal-to-noise ratio, but the bandwidth became smaller and smaller. And on the other hand, if we have a very small detector, we have huge bandwidth, but our signal-to ratio is small. So the question is, which negative effects outweigh which one? And in our research, we figured out that there is an optimum value of the detector where the negative effects of the bandwidth doesn't affect the performance of the system as much. So we modeled our system on the transmitter side. We'll just consider some light source. There is usually two types of beam that are used in communication system. Is Gaussian beams and beams with uniform distribution. For uniform distribution, is just the received power of the detector will be just a relation between the detector size, which is AD, and the beam size, which is AB. We will also consider that the beam has a certain angle of the divergence. And you can see that the path loss is actually sort of hidden in the beam size, because we have a certain distance from our point to our detector, which is going to be D, and certain angle of divergence. And if we open up the sort of AB, we can see the path loss there. For the Gaussian beam distribution, the expression is a little bit more difficult. We have also transmitted power, which is times 1 minus exponent of this, the same relation, which is also what the path loss is. For uniform distribution, it's very easy what's the beam size going to be, because it's just we have the uniform intensity throughout the beam, and then it falls to 0. For the Gaussian beam, we will consider the beam size is a certain area with a radius, let's say R0, where intensity falls down to the 1 over E square of the picoradians, which is roughly in percent, or it's 13.5%. On the receiver side, we will consider a photodiode. You can see an equivalent circuit of the photodiode. And the photodiode, the same as LEDs, has a low-pass nature. So we can express the bandwidth of the photodiode as 1 over 2 pi RS-CS, where RS is a source resistance and CS is capacitance. And you can see on the bottom left that the detector size and capacitance are proportionally related, while on the with the bandwidth is reversely proportionate. And that's where sort of the trade-off comes in. And there are different strategies to model this system and to model this solution, because the user may, not the user, the one may choose to use only the bandwidth of the photodiode, because the noise is flat below the 3 dB bandwidth, so no filtering needed, no noise enhancement is occurred. More commonly used approach is a photodiode and transimpedance amplifier, which can boost our bandwidth, can boost our noise performance. You can see the equivalent circuit on the bottom. Also, there is the case of segmenting photodiodes. You can see that, well, roughly, you can see that how much the signal-to-noise rate changes with for different segmentations of the photodiode. And of course, there is the third approach is using different modulation strategies. It can be MPAM, that's what we use. It can be OFDM, and let's say power allocation also allows us to use more effectively available bandwidth. For our system, we will use for our approach, we'll use M-pump system. And for this particular presentation, I will only show the results for when we use the bandwidth only of the photodiode, and we use just a matching impedance amplifier. But we're already working on the other approaches and the PD plus TAA and the other modulation strategies. For M-pump system, it has its own advantages with the cost, with the low power consumption, and the throughput can be seen as a through the Nyquist equation, which, if we open up, it can look like a Shannon-like equation. But with because it's derived through bit error rate and with the introduction of modulation gap, we can sort of use it. We can use it in our case. But what particularly is interesting for us is how the detector size impacts the performance of the system, so the bit rate. And you can see that on the bottom left that detector size and the bandwidth is reversely proportionate, and we have it like directly proportionate to the bit rate. And under the logarithm, we sort of have cubed detector size. And the question is, which one outweighs more? The results are very interesting because we also limited ourselves by 2.5 milliwatts because it's a limit for eye safety for visible light communications. Of course, if we're going to use infrared, we can boost up our powers and, of course, increase our signal-to-noise ratio. And this particular plot is for uniform distribution because the Gaussian distribution gave pretty much the same result. And what's interesting about this, that's for strong signals, so we have like for 2.5, the optimal value of the detector much more clear than for weaker signals. Also, the detector size is a little bit smaller than for weaker signals. And that's because for the weaker signals, this relation, these negative effects almost cancels itself. So we have much flatter curve on the bottom for weaker signals, which is, for our case, 1 milliwatt. But for the strong signals, it's and for weaker signals, we have sort of more tolerance while designing a system because we can move the detector size sort of a little bit to the left, a little bit smaller, a bit larger, without drastically changing the performance of the system. While for stronger signal, it's otherwise. So in the conclusions, we figure out that there is an optimal detector size for non-imaging. What all this was done is just for non-imaging systems. There is an optimal detector size if we use the bandwidth of the photodiode. We strictly use the bandwidth of the photodiode because the noise is flat. But what I can also say, because we're already working on the other results, for the other strategies for the PD plus TAA, so if we include transimpedance amplifier or if we include different modulation strategies, there is also an optimal detector size. It has its own intricacies, but there is also an optimal detector size for other cases. But for this particular case, the noise is flat below 3 dB bandwidth, so it's much easier to calculate and to simulate. And the optimal detector size depends very much on the parameters of the system, so the beam size, the beam size, the path loss, the internal components, the internal characteristics of the photodiode, so its source resistance, its capacitance. And as you saw, for weak signals, the optimum as less clear as the negative effects almost cancel each other. And for the next steps of this research, we are planning, of course, to include imaging system to see, because it will definitely improve the signal-to-noise ratio. So we sort of gonna see the more flat curve on the for larger detector sizes. Include transimpedance amplifier into our design, which is going to improve the bandwidth and noise performance of the system, and also try to see what other modulation strategies will bring into our research and into our results. How, let's say, power allocation will affect our system. That's it. Thank you for your attention. And if you have any questions, I would be happy to answer. Thank you.